Okay, the second video for section 8.1, sequences. We start off with this theorem here, 12.4. If the limit as x goes to infinity of f of x is equal to L and f of n is equal to a sub n whenever n is an integer, then the limit as n goes to infinity of a sub n is equal to L. So in other words, what we're saying is this. We take a sub n, which is a function of positive integers, or really just integers, but usually positive integers, n equals 0 or 1 going up through infinity. And if we can rewrite n as a continuous, or a sub n as a continuous function, f of x of its variable, then whatever limit f of x has, a sub n has to follow suit. So that's our workaround. F of x, and x is when x is a real number, that includes, and x is typically used as a continuous variable, so it's usually any real number in the domain of the given function. So if we were to go from 0 to infinity for x, that would be 0, 1/2, 1/4, 1/5, e, 1 over e, pi, 1 over pi, all the rational numbers and irrational numbers that are, on the number line from 0 through infinity. However, a sub n only takes on integer values. So f of n is 1, 2, 3, and 4. So of course, for the continuous variable, f of x being a function of the continuous variable, it's going to include the f of n's that show up when n is 1, 2, 3, and so on. So this is actually a more powerful limit to evaluate, a more general limit to integrate than this one. So we'll just use our knowledge of evaluating limits of continuous functions or continuous variables towards evaluating the limits of sequences, which means that all the tools we had for those old functions we can now use on sequences. But we should be careful to change this, at least formally in the notation, to a function of a continuous variable x before we do that, because that's technically what's happening. So f of x is equal to x over e to the x is what we rewrite our given questionable sequence limit of a sequence as. So x being that continuous variable, and now we're looking at the limit as x goes to infinity of x over e to the x. Now we know that for all the whole numbers, when x is equal to one of the whole numbers n, 1, 2, 3, 4, and so on, then it matches our sequence. Okay, so if this thing has a limit, then so does our sequence, and those limits are the same. Now, we look at x going to infinity, and well, the numerator goes to infinity then. E to the x, it also goes to infinity. So we have infinity over infinity in this case, an indeterminate form. It's a ratio, so we can use L'Hopital's rule immediately. We take the derivative of the top, which is 1. We take the derivative of the denominator, which is e to the x, and we take that limit overall now. Now, as x goes to infinity, the top remains fixed at 1, the denominator runs to infinity, and that drives the whole expression to 0. So since that limit exists and this function matches this function for all whole numbers plugged into x, then we can conclude that the limit of our sequence is also 0. So the limits will match. It's guaranteed by that theorem. Okay, now we'll be a little bit less formal as we work on these, but it's still encouraged that when you go from here to here or from there to here, that you still change the variable so that way you're at least giving a nod to the fact that we're switching from a discrete variable to a continuous one. So let's see another example, maybe one that's not so easy. There's a squeeze theorem. So that's yet another tool that we can use, very similar to functions of continuous variables. If we have 3 sequences, a sub n, b sub n, c sub n, and b sub n is between a sub n for every one of their terms, n equals 1 through infinity, or for all n greater than some capital N, so maybe eventually b sub n is always between a sub n and c sub n, then we have this limit relationship right here. Oh, sorry, and we need one more fact. A sub n and C sub n need to match in their limit. They need to share the common limit of L. In other words, the bounding sequences below and above have the same limit L that forces the sequence in the middle to have that same limit L as well. Okay, so let's have a look at a nice use of this theorem below. So we have the sequence a sub n is n factorial over n to the n. Remember that n factorial is equal to 1 times 2 times 3 times all the way up to times n. Okay, so that's what that means. So this is a really good question. These numbers can grow quite quickly, right? Factorials seem like they'll grow pretty quickly, but we also know that exponential functions grow quickly as well. And not only is that exponential, it's got n in the base as well, so that's growing large as well. So there's a little bit to think about with this. Um, pause for a moment here and try to do this without looking at any of the work below and just imagine which one grows faster. What you might do is experiment a little bit. Plug in n equals 2 and see what you get. Plug in n equals 3 and see what you get. That's no way to prove it, but it's at least, you get to get your hands on this sequence and get an idea of what it's doing. Now to actually prove this, what we want to write out is a sub n as its factorial in the numerator. We'll write that all the way out to 1 times 2 times 3 times n minus 1 times n for all the numbers in between. And then there are n factors of n right here. So n times n times n times. That's thanks to n being in the base and then n being the exponent here. And then we want to realize what kind of bounds we might be able to put on this. The one thing that we can see right away is that all of these terms, 2 over n, 3 over n, n minus 1 over n, n over n, they're all less than 1. So if we multiply a bunch of numbers together that are less than 1, then their product is less than 1. Okay, we've reserved this 1 over n off to the side because we'll use that as a bound potentially. So in the next line, we'll see what we'll do with that. We know that all of these, if we make it up to, I don't know, say n equals 10, then we know that every number that was in this numerator, 2, 3, 4, 5, 6, all the way to 9 and then 10 over 10, when we multiply all those together, they're all less than 1, and that result is less than 1. And that's going to be true for any n, not just 10. That was just an example to help convince us. Okay, so we also know that this sequence is bigger than 0. So a sub n is always greater than or equal to 0. So that's a useful fact. Now, a sub n is less than or equal to 1 over n. That's because a sub n is equal to 1 over n times a bunch of things that are less than 1. So it might not be precise to just say, this is less than 1, but it's enough. It's all we need. If all of this stuff is less than 1 over here, then we know that if we just write a sub n on the right, 1 over n on the right, that a sub n has to be less than or equal to 1 over n. Think of it like this, maybe. To the right of this is, times something that's less than 1, times 1 potentially, right? Okay, so a sub n is less than or equal to 1 over n, and a sub n is greater than or equal to 0. We have a left bound, we have a right bound. Now, if both of these bounds, in other words, this one as a sequence, which is just the fixed sequence 0, so it's 0, 0, 0, infinitely many times written down, and then this one is 1 over n, it has a limit as n goes to infinity of 0. That's nice. These things are written down below. The limit as n goes to infinity of 0 is 0. The limit as n goes to infinity of 1 over n is 0. So now they both have the same limit. A sub n is trapped between the two of them, thanks to this and this inequality. So the squeeze theorem implies that the limit is equal to 0. This term is in between each of those other two sequences. Both of those sequences approach 0 as n goes to infinity. Now, what does this mean? Which one's faster, n factorial or n to the n? Well, if n factorial was the faster one, it would take over and drive this to something larger than 0, and it should drive it off to infinity. But n to the n seems to have driven this to 0. It seems to have taken over. So the one that grows faster, two sequence terms that grow faster, is n to the n itself versus n factorial. But as a sequence together in a ratio like this, we just have this this limit of 0 as n goes to infinity. Now let's see further tools. First, a definition. We have monotonic sequences and bounded sequences. So first we see monotonic. That's increasing, decreasing, or strictly increasing or strictly decreasing. Strictly increasing means there's no less than or equal than signs, or equal to. There's strictly decreasing is there's no greater than or equal to. Just increasing or just decreasing, we have the weaker inequalities. So we allow equals to or equals to. Okay, so let's see some examples of these. A sub n equals n. We're asked to classify whether or not this is increasing or decreasing. Well, each one of these n's is 1, 2, 3, 4, and so on. None of them are equal to each other, so we know that this is an increasing sequence, strictly increasing, because 1 is strictly less than 2, is strictly less than 3, and so on. Now, an increasing or strictly increasing sequence is an increasing sequence, right? Just because it does meet that criteria. So strictly increasing is a stronger situation. So we'll of course, reserve that for that stronger scenario, but just note that strictly increasing is also increasing. And similarly for decreasing is strictly decreasing. Now a sub n equals 1 over n. That's 1 over 1, 1 over 2, 1 over 3. Those are decreasing. None of them are equal. So this is also strictly decreasing. We do not have equals to for any of them. Okay, now let's see. Negative 1 to the n times 1 over n. So this will be negative 1, positive 1/2, negative 1/3, positive 1/4, and so on. Now think about this. Even though the magnitude of these is decreasing to 0, as governed by the 1 over n term, we still don't quite have that it's decreasing or increasing. Think about the fact that negative 1, we have to increase to get to 1/2. Then from there, we have to decrease to get to negative 1/3. Then we'd have to increase to get to 1/4. So this is not monotonic, or non-monotonic is another word we might throw around, but it's not increasing, it's not decreasing. So it is not a monotonic sequence. Okay, maybe a few different ways to say that. You might see other language in the homework, but monotonic is commonly used. So for this sequence, we have 1, 1, 1/2, 1/2, 1/4, 1/4. Looks like it's going to double each of its positions. Note that between 1 and 1, 1 is not strictly less than 1. It's not strictly greater than 1 either. So, but as we go from 1 to 2, or 1 to 1/2, it looks like we decrease. And then again, we'll decrease from 1/2 to 1/4. But we don't strictly decrease because between some of these, we can have an equal sign. So the most appropriate fitting equals sign between here is less than or equal to, less than or equal to, less than or equal to. So this is a decreasing sequence, not strictly decreasing, just decreasing. Lastly, we have a sequence that never changes. It's 5, 5, 5, so on infinitely. So that's a constant sequence. And this one actually satisfies increasing and decreasing because less than or equal to or greater than or equal to fits between each one of these 5s and is still true. So a constant sequence is both increasing and decreasing. Of course, it's not strictly increasing or strictly decreasing though. Okay, so those are just some definitions. Now we'll use this idea of increasing or decreasing to help define another version of convergence or some other rules for convergence. So a sequence being bounded is the next thing we need to know. A sequence is bounded above if for some real number m greater than 0 such that a sub n is, A sequence is bounded if there exists a real number m greater than 0, such that a sub n is less than or equal to m for all of its indices. So every single term in the sequence is less than m. Similarly, a sequence is bounded below if all of its terms are greater than or equal to some m, some real number. In this case, we're using real numbers that are greater than 0. This is useful for sequences whose terms are all greater than 0. And generally, we'll be able to angle things to work out in that way for us. And we'll see that later on when we start to look at series. So if a sequence is bounded from above and below, then we say that that sequence is bounded. So above and below, having bounds above and below is a bounded sequence. If neither, if it's not bounded above or below, then it's said to be unbounded. Okay, if it's unbounded on one, if it doesn't have an upper bound, or if it doesn't have a lower bound, we'd say that it's unbounded. Okay, so if a sequence converges, then it's bounded. That's one nice fact to have around. It's not exactly what we need, but something similar to the converse of that. We just need a little bit more information to get this. If a sub n is increasing and it's bounded above by m, then the limit of a sub n is less than or equal to m. Well, namely, also it converges. Okay, so if it's increasing, but it can't get larger than some value m, then of course it has to converge. It's got a ceiling above it, and all those points that are moving towards that value of m are trapped below that, but they still have to increase towards it. So that's going to converge. Similarly, for decreasing and bounded below, then the limit exists, or in other words, the sequence is convergent, and we at least know this bound on its limit. We know that its limit is greater than or equal to that lower bound. Okay, so let's use this in one final example as a tool for showing convergence of a sequence. So we've got the sequence a sub n is equal to root n plus 1 minus root n. Does it converge or diverge? Be very careful. Don't just apply the limit to this right away, because if you did and said the limit of this minus the limit of this, you'd say infinity minus infinity, something like that. And this is where we get in trouble. We cannot do algebra with infinity. So this is really more or less undetermined right now. We don't have a limit law that can help us out of this. So what we should do is first convert this. Well, of course, we're going to try to use our situation, the theorem from the previous page, show that it's bounded either above or below, and that it's increasing or decreasing respectively. And if that's the case, we can show that it's convergent, at least state whether or not it's convergent. We might not be able to find what it converges to with that theorem, but we're only asked for convergence here. So first, is it increasing or decreasing? Well, if I'm not sure about this, I can prove it handily by saying, let's convert it to a function of a continuous variable. In other words, replace n with x. Now, the first derivative test will tell me whether or not this is an increasing function for x values that are greater than or equal to 1. Right? This sequence is only going to work for n values that are greater than or equal to 1. Or 0 maybe, but one term won't throw anything off. So the derivative of this function f is given as follows. Now we realize that this is less than or equal to 0 for all x values greater than or equal to 1. How do we know that? Well, we know that square root of x is less than the square root of x plus 1, but when we flip them, so have 1 over the square root of x plus 1, that's actually less than 1 over the square root of x. So their difference, this number, is less than the one on the right of the minus sign. So we've got less than or equal to 0 here. So we know that its first derivative is negative for all x values. So this is a decreasing sequence. F prime is negative, so f decreases. This means that a sub n decreases. It follows suit. The discrete a sub n sequence follows suit with the function of the continuous variable. Okay, next up, we observe that root n minus root n is greater than or equal to 0 for all n. And the reason we know that, again, this is given in the explanation, and this is a really well-written answer in that regard. Everything is justified. If you're not sure, show a step to justify it. Add a line to justify your claim. We know that this is greater than or equal to 0 because square root of n is greater than or equal to the square root of, square root of n plus 1 is greater than or equal to the square root of n for any positive integers n. Okay, in fact, maybe I need to be a little bit more clear right here. Let's say for all n greater than or equal to 1. Okay, that does a little bit better job. All right, so thus a sub n is greater than or equal to 0. Our sequence term, remember, is this. This is a sub n here. It's greater than or equal to 0 for all n values greater than or equal to 1. Now that's good. We've justified that this is the case. Now that we have that the sequence is decreasing, so a sub n decreases, and it's bounded below by 0, theorem 1210 from the previous page confirms that a sub n is a decreasing sequence, that since a sub n is a decreasing sequence that's bounded below by 0, a sub n is therefore a convergent sequence. So if you read the language of that sentence, you have a better version of what I just sort of paraphrased. So that's it. Those are all the tools that we'll have and we'll need to show convergence of sequences. The only reason we'll really work with sequences is because they help us assess the convergence of series. The difference between a sequence and a series is that in a series, we're going to add up all the terms of the sequence, whereas a sequence is just a fixed list. So we'll see that in 8.2.